What is up, fellas? Welcome again to my channel, whether you're a new or an old friend. This channel will post one lead code a day based on either a theme or a random choice. Basically, I'm going to be studying with you guys together on a lead code problem I've never attempted before. That's right, there's no prescripted answer. We're on the same page here, but don't worry, I got you covered. And we'll crack each of these problems together like brothers and sisters. I come from a non-computer science background, so I'm no better off than most, if not all of you guys, in terms of coding knowledge. But that is okay. We'll grow knowledge together as we move on to crack more and more of lead codes. You can think of this as a first person gameplay of me trying to walk through the lead code set. And who doesn't like first person games, right? So without further ado, let's start today's coding problem. Today we'll continue with our series 1, everything about dynamic programming, and the lead code problem is lead code number 70, climbing stairs. Let's get into it. Okay, here it is. Number 70 is a pretty early problem in the lead code set, so it should be fun. Climbing stairs, easy. You are climbing a staircase. It takes n steps to reach the top. Okay, makes sense. Each time you can either climb 1 or 2 steps. All right, so you can have different strides, I guess. You can just take 1 or 2 steps. Yeah, makes sense. In how many distinct ways can you climb to the top? Oh, okay. That sounds like an interesting question. In how many distinct ways can you climb to the top? So this is like what, statistics or exhaustive search, things like that. All right, here we have some examples. Input n equal to 2, output 2. Why? Because if there's only 2 stairs, we can have 2 ways to climb the stairs. 1 plus 1 or 2. Makes sense, right? Let me just try to, guys, visualize that with our with our diagram here. So let's say we draw our staircase. Okay, uh, 2 staircases, right? So this is the ground, 1 step, 2 step. That's a 2 staircase. So how many ways do we have? First is we go here, and then we go here, right? That's number 1. Second one is that we just jump 2 stairs at a time. So this is number 2. So overall we have 2 different approaches. That means if n equals to 2, then the answer should be 2, right? Let's just move on a little bit just to see what we have when we have 3 stairs. 1, 2, 3. All right, so let's start from the basics. Just 1 step at a time. 1, 2, 3, right? So that's number 1. And we can throw in some 2 steps towards the end. So another one we could do 1 and then 2. That's our solution number 2. Uh, what else can we do? Well, we're left with the choice of, doing 2 steps in the first walk and then 1 step at the second walk. So 3. That means if n equals to 3, our answer is also 3. Coincidence? Yeah, kind of like a coincidence, I think. When we have 4, that will become more complicated. We'll probably have more steps. So when n equals to 4, we're not going to draw these staircases anymore because it's going to get messy. We're just going to count. So we can do 1, 1, 1, 1, right? We can also do 1, 1, 2. We can also do 1, 2, 1. Excuse me. We can probably also do 2, 1, 1. What else? We can also do 2 and 2. So that's 1, 2, 3, 4, 5. So our answer this time is equal to 5. Right. So now answer starts to be larger than the staircase numbers. And we expect this answer to grow faster and faster when the number n increases. But basically, that is the idea. All right, let's go back to our problem. And we have constraints. Remember from last time, if we actually know the maximum number that Leetcode is going to test us, we can save ourselves some storage space, and we can pre-compute all the answers to make our solution faster. I think we're going to use that trick this time as well to start it. All right, so like before, we're going to start first with our um, prototype, and we're going to just basically copy the problem description and create a new um, Python notebook. And we're going to call this problem 70 climb stairs, right? And this is the description, right? And also we want to include a little bit of the code as an example. So we're going to do here this, right? So, okay, we better use the code syntax to make sure that it's not interpreted as a markdown. Right. Now, how do we solve this? We definitely have a class, and we have class solutions. So yeah, we're gonna start with the class definition because that's what we're better off with. Uh, and Leet 509, here we go. Class solution, right. Um, we are going to use the class definition here. So we're gonna just copy that, go to our notebook, probably rename this as well. Rename Leet 70. All right. So solution class, climb stairs. Here we start our definition. And in the next section, we also want to have our test cases, right? Test cases. We always need to build our test case. So we're going to build a solution object, solution, and we're going to do some test cases. For that, we can reuse some of the syntax here. And we're going to basically maybe, yeah, make 6 or 7 test cases. And then, oops, and then modify the contents here. As you see, climb stairs. And then let's just hand calculate some of the answers. First, what is the range? Again, the range, this is important, 1 through 45. So we want to also put that here. This is very important. Okay, so we don't have the input 0. We just start from input 1 all the way to input 45. So input 1 expects answer 1, input 2 is 2, input 3 is 4, 4 we're expecting 5. When input is 5, how many are we expecting? Let's hand calculate, okay? Let's hand calculate that answer for ourselves. So, yep, in order to build our test case, let's hand calculate that. Is there a glitch? Okay. Say we have n equals to 5. Let's see how many ways of climbing the stairs we can have. 1, 1, 1, 1, 1, of course. And 1, 1, 1, 2. And we have 1, 1, 2, 1. And we also have 1, 2, 1, 1. We can also do 1, 2, 2, right? Yeah. And then we're left with this 2, 1, 1, 1. We also can have 2, 1, 2. And lastly, I think we can still do 2, 2, 1. Right. That's everything, I do believe. So we have 1, 2, 3, 4, 5, 6, 7, 8. And our answer is 8. Okay, so we have expectation 8. Yes. And when I just think of an idea here. Stairs, you can actually break uh, break a very large stair case climbing problem into like two sub problems because they're all the same, right? For example, let's say this is just an idea, like maybe this could be an idea for faster calculation. Say if we want to break down um, the five staircase, one, two, three, four, five, into simpler problems. Um, we can probably break up in the middle, right? Like this is one, two, three, four, five. We're gonna look at number three and try to break it from here. Then there are of course two cases. Case one is that you actually step on three, and the second case is that you skip three, right? There's only these two possibilities. And if you step on three, that means whatever you do before, you're gonna step on three, and then go from three and move on. And it's basically become a problem of n equals, I guess, one, two, and three. N equals to three, uh, plus a problem of, let's say, one, two, n equals to two. Right, n equals to two. So this becomes, it's decomposed, right? The problem is decomposed into an n equals to 3 problem and an n equals to 2 problem. And if we skip number 3, that is also like interesting because now, um, let me just, yeah, remove a little bit of the mess here. How do we do that? We can remove that arrow. Yep. And basically it means you skip 3, so you have to land on 2 and 4 because we can only do a maximum stride of 2. So we definitely stepped on number 2, and from 2 onward, you definitely did a um, 2-stair stride, and you landed on number 4. So this becomes this separates the problem into even simpler sub-problem bits. So you had a 1, 2, you had a um, um, let's say a m plus 2 problem actually because you landed on staircase number 2, and then um, all the way from 2 to 4 is known because there's only one way to skip number 3. Uh, and then from staircase number 4 to number 5, it's an m plus n equals to 1 problem. So in total, that is how many numbers of problems, numbers of ways to cover the staircase that we can get. So for any larger problems, we can just break it down into these two parts, right? Uh, and why did we try to separate at 3? Because this 3 is like the medium of 1 through 5. It's better to separate in the middle. It breaks down the problem evenly. So I think this is one first heuristic we can do. And you know, this leads to a reliance on pre-computations. And this is exactly something we can do. We can use DP for. And DP is like relying on previous calculations to build up, a more complicated computation so that we don't need to recompute any of the essential steps for more complex problems. And okay, so this sounds like a good heuristic. And how do we implement it? Well, let's use another page and move on. Right. So hold on a second. I'm gonna use a blueprint. Um, so we're gonna build break down our staircase problem into this. So uh, text size. Can we make it larger? Uh, so staircase problem breakdown. Uh, right. We just want to make our test larger. Normal. Yeah. Uh, fixed size. Uh, line width. Line height. Yeah, this sketch.io, not so familiar with what it is. How can we make this text size larger? This is, here we go. You just drag and drop. All right, staircase problem breakdown. Now, let's break the problem down. And please let me know in the comments, do you like the red color versus the blue background? I'm kind of okay with it, but if you think, a different color works better visually, let me know and I can adjust accordingly. For example, we can use black as well. We can use red, we can use black. Um, let's try black this time. See if it actually makes more sense. Or yeah, we're gonna use black, and then we're gonna staircase break down the staircase problem here. So how do we break it down? So of course, uh, the spirit here is to use the bottom up approach, right? Uh, bottom up approach, so that we're gonna use a lot of pre-computation. Pre-computation. I think we can rely on that. And because we can exploit the fact that we know the constraint, the maximum number we're going to be dealing with in Leetcode, we can definitely do some pre-computation. So what this is going to look like, it's going to be like this. Um, we calculate, the staircase n equals to 1, right? Um, let's just use like 1 and a circle to represent case n equal to 1. And then, yeah, this is like the basic building block. And then we calculate number 2. Um, right, so number 1, number 2. And then we're gonna use like kind of like an recursive expression from number 3 on. For example, when we have um, n equals to 3, what we can do is that we can use this recursive relationship. Um, the answer of n equals to 3 is going to be a combination of two answers, right? Because we are basically using the recursive relationship. If we look back at this, you see we're breaking it into two cases. Whether we step on the medium staircase or we skip the medium staircase. So that is the idea or heuristic. Uh, and here we go. So we can name this as, I believe, let's say this is step on medium, right? And then another one is going to be called skip medium. Skip medium, yeah. And so we're going to add those two cases up together. And they do make up a complete decomposition. So what does step on medium mean? Um, step on medium, so let's just use some visualization here. Um, so we have, oops, not that. So we have three staircases, one, two, three. And this is number one, number two, number three. Step on medium, that means we're stepping on number two. Skip medium, that means, you know what, we are stepping on number one and number three. Uh, yeah, so that is the breakdown of it. Because luckily we only have, this is all possible because luckily we only have two ways of, two different strides. So stride can either be one or two. That's why we can break it down into these two cases. Otherwise, if we have strides equal to one, two, or three, we may need a third case or something like that. So let's just go on to distill this recursive expression to work it out. Um, so when we do step on the medium, how do we break this down? Is this gonna be like, yeah, if we step on the medium, we basically uh, have let's see, broken this down into a problem of like uh, uh, A2, right? Because now we're looking at the problem of going from 0 to 2 and then 2 to 3. So this becomes A2 plus what? Plus A1. We're going to generalize this later, all right? And if we skip medium, this will be like going from 0 to 1 and then going from 3 to 3. Uh, so 0 to 1, that is a problem of A1, and 3 to 3, that is a problem of nothing. It's like a certainty. So let's say plus 0. There's nothing. Plus nothing. So just A1. So this is like a breakdown. But is it general enough? Probably not, because we need to also take into account the difference between even and odd numbers. Because when n equals to 4, now this is a little bit different in terms of the case. We still have these two brackets representing this step on medium or skip medium. But now, since we have four staircases, one, two, three, four, right? So 0, 1, 2, 3, 4. Things might be a little bit different because now the medium here is neither 2 or 3. It's like in the middle here. So that's kind of a weird thing, right? Because now it doesn't even mean anything. It's like in the middle of 2 and 3. So how do we then separate them according to this middle of nowhere staircase number? Uh, well, yeah, this is the thing. We need to come up with a new rule for when n is an even number. How about let's just say if it's like in the middle of two staircases, we just go to the left, like the lower one. Um, that could be a way to do it. So we'll do it. Um, we'll say that this is gonna be split at number two, and then if we skip number two, we will basically land on number one and number three. And yeah, this medium now for number four, it means two. For number three, also the medium means two. This is just like a rule we're making up. As long as we make sure that this rule is a generalizable, it's fine. So step on medium, this means we go from 0 to 2. It's the same case as before, so this is still A2 plus A1. What about skip medium? Skip medium meaning that for the first part, we're going to jump from 0 to 1. 0 to 1, there's only one chance, but mathematically, it's A1. And then we go from number 3 to number 4, and mathematically, that is another A1. You know what? We can think, just to make it more make it more general, we can just say it's a zero. We'll just make this equal to zero, right? So now, even for n equals to 3, we do have a general expression. We just say hey, a0 is 0, and that's it. Uh, right, and now I think we are confident about n equal to 5, right? Because now we can apply just similar logic here, just by following what it is. So let's just uh, write out following this trend here. Um, we have now a5. So this is we're gonna first find the medium number. For 5, the medium number is 3, and then it's gonna be uh, one number less, so a2. Uh, I'm just reading from the two previous cases there, and then this here is gonna be like what, a yeah, a1 plus a0, a1 plus a1. This is kind of interesting because what should I put here? I'm pretty sure it's gonna be like just one number larger than a3, so uh, a2 plus a1. I'm just thinking that it's gonna be like this. Uh, and then let's see, what about n6, a6? I'm just gonna follow the example of n equal to 4, okay? So this is gonna be like a3 um, plus a2, the same, and then we're gonna plus um, a2 plus a2. Right. So this is like kind of like the rule that we worked out. Do we have a general expression? Um, yes, I think we can have a general expression. I just need to move everything up a little bit so that we have more room down here to write down the general expression. Here we go. We made some room here. And the general expression, here we go. The general expression, let's maybe use a different color to uh, outline, to yeah, to stress it. We're gonna use dark red. Yes. Uh, when we have n equals to uh, k, and when it's odd, right? Um, so ak equals to uh, ak minus, no, it's not minus, but you know, k plus 1 over 2, right? That's a relationship between 5 and 3 here, and 3 and 2 here. Right. So that's like the medium, and then plus a k minus 1 over 2, right? And then plus uh, the next one, this, what is this? This is like 2, 2, 3 is like one number less than 3 because this represents, um, the the lower half of the separation. Excuse me. So it has to be one number less than the medium. So yeah, so this is a um, half of k minus 1, I'm pretty sure. And then for the upper part of the division in an odd number case, uh, we're gonna have the number even less than this, uh, and it's one less than this number here. So it's k minus 3 divided by 2. That's when k is odd. And what about when k is even? Even? So our AK, the generalized expression, is going to be, now because k is even, uh, k could be, k is divisible by 2, and the medium that we choose to use is simply k over by 2. That's our choice. Um, and then, of course, the next one um, is 1 less than k over by 2, so it's going to be k minus 2 over 2. Uh, and then we're going to plus the second half, the upper part of the separation, the division, uh, is going to be, yeah, so this first number here is 1 less than the medium. So we're going to say a k minus 2 by 2, and then plus, uh, it's the same number, so a k minus 2 by 2. Um, we can definitely simplify this a little bit, so we're going to write it as, because you see we have 2 of these here, uh, so we can do what, um, 2a half of k minus 1. um, Wait, there's actually a k minus 3, so yeah, I think we need to move this to the middle because it's a value in the middle, and we're gonna write uh, a k minus 3 by 2 plus this plus a, yeah, there's not much room here, um, k plus 1, right? And then this one here, we have actually a lot of k minus 2 over 2. So this is actually simpler in terms of expression. So this will be uh, 2/3 of a k minus 2 over 2 plus 1. Sorry, it's not 3 over 2, it's 3 of them. It's 3 of them, and yep, plus a k over 2. All right, so we have our generalized expression. Um, so this generalized expression is the recursive relationship for us to calculate, more and more complicated values. I hope it's correct, but we can verify it. We can verify it by implementing this quickly in our class-based calculation. Now, how are we going to do that? So, um, we're gonna we're gonna build a pre-computation that um, computes all the values up to 45, and then we're just gonna look up. And for lookup, we're gonna use a dictionary, right? So, yeah, let's just say that, uh, count the number of ways to climb and stairs using a medium stair separation and dictionary based uh, dictionary storage stored DP pre-computation. Um, right, and our the iterative relationship right? So we use A to represent our answer. So AK, AK equals to, according to ourselves, um, 1 of A K minus 3 over 2, right? So yeah, so when when K is odd, uh, and then what, plus 2 of 2 times uh, uh, K minus 1 over 2 plus 1 of K plus 1 over 2. When K is even, this is when AK equals to, according to our previous computation, 3 times of what, a let's take a look. 3 times of K minus 2 over 2, K minus 2 over 2, plus 1 of a K over 2. Right. So K, yeah, K is like the n, right? Yeah, this is, we have K is greater or equal to 3. Yeah, this is like, uh, so K equals to 3, 4, 5, etc., etc. Let's put it here. Whoops. K equals to 3, 4, 5, etc. When K is even, K is odd, right? So that is our iterative relationship. But it's not going to be implemented here. In this main function here, we just look up. Uh, and so how do we look up? Well, if it's a dictionary, how do we look up dictionary? Um, let's first, store it like stored dictionary. We initialize it like that. We just say storing storing the calculated results uh, like what, like we have, again, we're going to use string of integers as our keys. uh, we're going to use a 0, sure, uh, and the value is 0, and then we're going to have 1, uh, and the value is 1, and etc., right? Yeah, we're going to do that. So how do you look it up? Well, mm, we're going to do the pre-computation, all right? So let's just call self dot pre-compute the results, pre-compute pre-compute solutions, and we're gonna pass an mmax to it, and we're gonna define our mmax as what, 40, 45. Okay, that's what you want. Let's do 45, and we're gonna pre-compute solutions, excuse me, and then it's gonna fill up the stored dictionary attribute with all those 45 solutions, and then you're just gonna basically look up. So how do you look up a stored dictionary? Well, you just return self dot stored will dictionary, um, and you're gonna look up the, ooh, am I stuck? Why am I not allowed to type anything here? Okay, temporarily frozen. uh, and then we use square brackets to look up on the keys of of the dictionary, and the key we're going to use is to turn the number n into a string, and that's what we have. Right, that's it for this function. But of course, we're going to define our pre-computation of solutions, and we're going to use this max here. And yeah, let's uh, make sure we document it correctly. The input type of max is integer. The return type, there's no return. We're just updating a property here. Uh, and also, we want a general description of what this function does. It is like pre-computing um, uh, pre-computing the solution for staircases up to n equal to n max. Right, that pretty much says it. And how do we do that? Well, two cases. We first have to look at our what we know with that this is like basically empty at the beginning. So we're gonna initialize the first two elements in the dictionary. So that means self.stored. Yeah, there's a dictionary I'm using for Japanese, so it always pops up. I don't know how to disable it here. Yomi-chan. Let's click it off as well as this. Yeah, so hopefully, yeah, they won't pop up anymore. Stored dictionary. Stored dictionary. Uh, so the first few, I'm going to initialize it. So this is like rewriting the definition. It's going to be the first one, of course, 0. It'll be 0. Uh, Actually, first 3, because we're treating 0 as an element too. And 1, this will be 1, 2. What was the answer for 2? It'll be 2. Okay, that's pretty much enough, right? Yes. So 1 and 2, we basically just use predefined answers. Since n equal to 3, we can start the recursion relations. So here we go. After that, we're going to apply the recursive relation to fill up to n equals to a max. And so how do we do that? Well, we can append a dictionary by basically say self.stored dictionary of str I equals to some value, right? And this is like some value, and this is going to be a for loop. So for I in range, we're going to start with uh, 3, right? And all the way up to n max. So in the range expression, it's going to be n max plus 1. It's just a nuance for the range input parameters. And the value, we already know that this is going to rely on this recursive relationship here. We're going to basically copy paste or actually cut that recursive relationship in here because that's where it belongs, right? And yeah, there are two cases. It's when k is even or k is odd. Can we? Does Python check if value is odd in Python? How do we do that? Mm, we want this to be fast as well. Okay. People seems to be using this expression, so I'll do that. If else works for me. So right after this for loop, if uh, equals to one, let's deal with the odd one first. So this is odd, right? I is odd. Well, since we've been using k all the way, we're gonna switch this to k so we can directly copy this expression here. And let's see. Um, right. But here's the thing. You see, um, the variable name a is pretty simple. But if we're using the stored dictionary uh, long name for that dictionary, it's going to be really, really lengthy for the expression. So change of strategy, I'm gonna just say a. Yeah, that's what I'm gonna do. Just gonna say a. This will make it fast. So a and right, right, yeah. And now we're gonna change the expression of this into the proper syntax um, for the dictionary. Right, so I hope this is right. Not really. Okay, this is correct. Uh-huh. And 2 times a of that. Right. Uh, now we just change this round bracket into a square bracket and make sure we turn the this thing into a string here so that we can use the dictionary to look it up. And here we have a, actually just string, and like that. Yep, this is just one of the two expressions. And else is when k is even. Here we should use k instead of I. And we will have a different expression. We're just gonna copy paste this pseudocode here. But now we're gonna make sure to use the right syntax to look up in the dictionary. And here as well, string, bracket like that. I think that is it. So yeah, I think this is it, and we can test it. All right, now let's test it. There's an invalid syntax, line 15. Oh, we didn't include the colon. Pretty bad. Okay, now we test some solutions. Well, okay. Uh, something is wrong. Oh, right, we didn't really change that from our template found our line. There we go. Test these. Well, name A is not defined. How come? Right. Oh, because yeah, because we need to be using the self prefix to call any class objects, class attributes. There we go. There's still something wrong. What is the key here? 0, 0.0. Oh, okay. So format string. Can we just use integer format of the string? Yeah. Because if we're looking at 0, 0.0, then of course we don't have that key because we have that 0 key, not 0, 0.0 key, right? Excuse me. So uh, let's see, Python str uh, yeah, integer to string format. Make sure it's just an integer. Uh-huh. Let's just debug a little bit. We're gonna print str of 0. Why is it not 0, 0.0 and why is it 0, 0.0 here? Um, oh, because when we're doing a division, we are turning that into maybe yeah. So this is actually a good takeaway. When you're doing division, we're automatically converting an integer into a double. So let's yeah, Python double to int. You can probably force the int function, right? I think you can do that. So let's do that. That's actually pretty smart. String, make sure it's an integer, right? And then string integer and string int, um, yeah, integer. Make sure we're turning things into integers uh, when we call them. Same thing here, integer. All right, let's see it again. Still, there's a problem. Name A is not defined. Okay. Uh, how come I missed out on that? Well, yeah, it's not really the same. Okay, here is the problem. I think we made a calculation mistake. Somewhere in our calculations, but theoretically, um, this the code at least it runs. That's a win. But now it's just the logic that we summarized from this sketch here. Maybe there's something wrong with it. Let's you know what? Let's just hand calculate a few of these numbers uh, and just validate our calculation. Okay. Uh, for example, mm, we can just test it ourselves, right? Um, using using a pencil. So now hand calculation of the recursive relation. So, oh, this is not code, so mark down. We have n equals to 3, so this is what we're going to use. We're going to have uh, a a2 plus 2 times a1 plus a0. No, this first one is a0 plus 2a1 and then plus an a2. And this will become a0 as we have assigned a 0 to it, and then 2a1, that is a 2, and a2 is 2. So this will be 4, which is correct. And I think we did it correctly here. Oh, yeah, I think, yeah, let's see. 4, right? So let's go back a little bit to our previous document. So we had, when we have n equals to 3, we should have a equal to 3, right? Because that's what the Leetcode is telling us too. 3 should output 3. Yeah, so it shouldn't be giving us 4. So this calculation is flawed, all right? And why is that? Well, mm, right, we need to get back to our sketch and work out the problem here. I think this was flawed. Now let's go back to this. And now we're going to start the correcting mode using red. When our n equals to 3, the separation is going to be like this. We cut at staircase number 2, and this is like, okay, step on medium. It's a problem of staircase 2. So there shouldn't be like a plus a1, right? Because why would you have to plus a1? Like from 2 to 3, there's only one way of doing it. So there's no plus a1. Why would you plus a1? Right? Yeah, so this is the one mistake we made. Okay. Moving on to n equals to 4. When we separate also at staircase number 2, um, yeah, so the problem is that, okay, um, on the lower half of it, we still have a n equals to 2 problem. So they also shouldn't be a 1 here, right? That's weird. When n equals to 5, right, there shouldn't be like an a2 here or an a2 here. That's weird. That's basically a mistake. And what about if we skip medium? When n equals to 3, we skip number 2 and we just arrive at number 1, and then we also jump to number 3 with the 2 stride. So with that, on the left side we have an a1 problem, and on the right side we already achieved we already at the top of the staircases. So this is 0. So this is correct. This makes sense. Um, and when our n equals to 4, right, we're going to separate at 2 as well. So we're left with a task of going from staircase number 2 to staircase number 4. So that would be a problem of, yeah, it would be, hold on, hold on. What am I saying here? Sorry. So we're talking about n equals to 4, and we're looking at skip medium. I was totally not myself. Sorry about that. So let's take a look at this n equals to 4 skip medium case. So if we are at n equals to 4 and we want to skip medium, So we need to land on 1, and we also need to restart on number 3. So these two tasks are exactly A1 and another A1, so this is correct. All right. What about n equals to 5? So n equals to 5, we're going to separate at a equals to at n3. Um, and uh, let's say, yeah, if we actually have an n equals to, I'm going to draw it. I'm going to draw an n equals to 5 case somewhere here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? And if we separate, um, if we step on the medium staircase number 3 here, our separation would be, first there's going to be like a n equals to 3 problem, and then there's going to be a n equals to 2 problem. So I guess, yeah, so I guess again I was wrong a few minutes ago by, just removing this. I think we still have uh, a problem of that. And I believe when we did this, this is also wrong. Yeah, so right. So let's recheck, n equals to 4. What we're pretty sure is that this really should be removed, right? Um, because although, I mean, when you separate it from here to here, this staircase 0 to 2, it is a A2 subproblem. Yeah, meaning n equals to 2, and you need to find ways to cover 2 stairs. But for the remaining one from 2 to 3, there is basically only one way of doing it, and you don't really add, right? This addition is meaning that, okay, you have an additional means of covering it, so you use addition. Instead, I mean, yeah, I think we should use multiplication here instead of addition. So yeah, that's the problem. Well, we're learning along our way, right? So it's actually a very big problem here. We should be using multiplication instead of addition, right? Because those are separate sequential tasks. What you do afterwards doesn't affect what you do previously. So this is a basic, I guess, um, probability or combination problem property. And yeah, sorry about that. I think I've not been doing combination problems for so long. I forgot like the basic principle about combination. So uh, for such combinatory tasks where you separate the task from somewhere in the middle, you basically make them into two subtasks that doesn't interfere with each other. And the fact that they don't interfere each other um, is going to mean that you definitely are going to be using multiplication instead of addition. Yeah, that is my bad. So we're going to use A2 time A1 here. And for the skip medium, we definitely need to use a multiplication as well. So yeah, it's going to be A1. If we skip medium, so it's going to be a subtask of 0 to 1. That's A1. And a 3 to 3 is an A0. Yeah. And what about n equals to 4? Now, n equals to 4, if we step on medium, right, number 2, which is number 2 by our definition, uh, we're going to have a problem of, we're going to have the two subproblems of 0 to 2 and then 2 to 4. So both of them are actually A2 problems. So I'm going to correct that, and this is going to be an A2 problem. And of course, we're going to use multiplication instead of addition. So I'm going to replace all of these with multiplication properly, right? And here it should be a multiplication as well. And we move it up into the bracket. And this one here as well. And we just said that it's going to be an A2 multiplied by A2. And here the same. It's going to be an A2 multiplied. Is it A1 multiplied by A1? Well, if we skip the medium, then yes, we have a 0 to 1 and a 3 to 4. So it's going to be A1 multiplied by A1, which will result in 1 by 1 multiplied by 1 is still 1. Yep, yep, that makes sense. Right, so we need to use multiplication instead of addition. That is the most critical takeaway and the most deadly mistake that we made today, guys. Uh, and I apologize about that, I guess, because that was a pretty bad mistake that I made. Now, let's recheck again when n equals to 5, and we're gonna basically be looking at here. We separate the medium number, which is 3, and then we'll have a task of 0 to 3, which is A3, as well as a task from 3 to 5, which is A2. Multiplication there, pretty solid. And then if we have, let's say, right, if we have a task of, if we skip the medium, so that'll be a task from 0 to 2, um, multiplied by a task of 4 to 5. So in that case, we'll have an A2, right, by multiplied by an A1. So multiplication, right? Uh, and let's look at uh, A6, all right? We're gonna move this up a little bit, and then look at how this should be. Just follow the trend here. What you can see here is that first of all, the immediate mistake we need to make is that we need to change all these plus signs into multiplication signs, right? And if we have 6 of them, then of course the medium is again 3 by our choice. And then we're going to be looking at a problem of, right, let's just draw it. I think it's still valuable to draw this in order to generalize. So A6, what we're going to have is this: 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and 0. So if we separate at the medium number 3, um, first half we have an A3 from 0 to 3. Second half we have 3 to 6, which is another A3. So here, I think it's a mistake to say it's A2. Indeed, it should be A3. And then what if we're doing like a jump? So we're gonna have two subtasks, one from 0 to 2, and then one from 4 to 6. So it's A2 times A2. That is fair, it makes sense. But so now the generalization that we made down here basically has to be completely rewritten, right? Exactly. So we know that when k is odd, like that, first of all, this is like a multiplication sign. And then in the second bracket, we'll have a k minus 1 over 2. Yeah, this is going to be a multiplication sign as well. Those are the changes we need to make. But then this simplification is completely wrong. There's no way to simplify it. Well, we actually still can. We can combine the common terms, or we can simplify it. But right before we simplify it, let's just move on the even case. When k is even, our a of k, for example, in the case of n equal to 4, is going to be the multiplication of two a2 and another a2. So it's again in the bracket, it's the medium number, k over 2, right? So here we can just say it's going to be a multiplication between uh, two identical numbers. And then for the latter case, it's also the same. It's two identical cases, and we just have a multiplication sign. And and yeah, this is it. And this first case, of course, can be a little bit further simplified. And we're going to simplify it as uh, so we just take the common term, k minus 1 over 2, right? And multiplied by the sum of k minus 3 over 2 and k plus 1 over 2. Right, there we go. And this is the new generalization of the recursive relationship. Let's just correct that here. It's quite different from previously. So now when this is odd, we'll have, let's see, right, we'll have this one and multiplied by the sum of these two, right? When k is even, it'll be the power, the square of this, and then the square of this. but we'll just write it in this form. All right, so this is the new relationship, and let's again implement them. Now self dot a, and make sure to look up the string integer of that, and then this is the sum. So in this sum we have two values. Make sure to use string integer for that. And also use self dot a string integer. All right, so that's the first one here, and the second one, when it's even, it'll be like this. I think, yeah, we can use power here. I think we can use power here. You just need to make sure that in the end, you know, the type of it is an integer, right? So, right, in order to just avoid the type conversion, we're just gonna skip the power thing. We're just gonna, because we don't know if, like, if we add a power to an integer, is it still gonna be an integer? Well, it probably is. All right, so let's just use it. So what is the expression for power? Like this? I think so. That's how Python interprets power. So self dot a str int brackets. Make sure I got it right. Yeah, and here it's another power. Yeah, we might as well just change it here, just to make it visually looking simpler. Self dot a. You know, if you'll be making a mistake like this during a coding test and not realizing the mistake in time, well, you're gonna waste about a half an hour, just like I did. That's definitely something you want to avoid. Um, so if you have actually watched this video from the beginning to the end, um, this may help you, you know, avoid similar, I guess, stupid mistakes like I did. All right. Anyways, we've just made it uh, hopefully into the correct form. But let me just double check. Python power operator. Python power of 2. Yep, that's how you do it. Yes. Reach the left value to the power of the second value. Yes. So that's how Python interprets power. I'm pretty sure. I just hope that this power operator is not going to turn an integer into a double, because that would be not intended. Anyways, I hope this is now okay. Well, not quite. Not quite, right? Still wrong. Why is that? Yeah, I'm still curious. So I think we still implemented something wrong. Let's again perform the hand calculation here. So if we follow the logic there, uh, this will be an A1 times what? This is A0 plus A2, I believe. Yeah, and this will be A1 because we know A1 is what? 1 times A0 is 0 plus A2. What is A2? A2 is 2. So this will become what? 2? Right. But I'm expecting 4. So what was wrong? Again, I think again we did something wrong. Uh, A3, A2 times A1. So that represents the case when we step on the medium stair, which is number 2. Uh, and how many combinations does that give us? Uh, A2, it's going to be 2, right? Yeah. And A1 is a 1. So 2 times 1. So there's like in total 2 different ways. Is that true? Because yeah, from 0 to 2 you have 2 different ways. From 2 to 3 there's only one way. So in total there's 2 ways in there. I'm pretty sure. Yeah. And if we skip medium, we will have what we call um, right. I see. This is one last mistake that I wasn't aware. This is wrong. We shouldn't be using A0 here at all because you see, when we have a skip medium, it's gonna be like 0 to 1 or and what? And 3 to 3, right? Yeah. So A0 because now it's multiplication, it's still gonna be 1. Like if you're already at 3, there's only one way to be at 3, which is just to do nothing, right? So that's what we're gonna change. We're gonna change this to 1. That's it. Yeah. Right. Let's just change this to 1, and hopefully we're now correct. And this hand calculation will give us 3. Yes and yes. I think now the expectations are met. Okay, so we have a seemingly correct interpretation of the answer. Let's send it to our Leetcode and see if it satisfies our requirements. So we're gonna basically copy the entire class definition here. Whoops, what did I do? Uh, so I'm gonna copy the entire class definition here and paste it into our solution. And we're gonna run code to test it. 23 milliseconds. Let's run some more test cases. Correct and correct. Okay, let's submit this. Right, it's accepted. Runtime is no average, but memory usage is a little bit less than ideal. Well, I guess there's definitely something maybe we're missing because we have used all the good best practice from our previous code example, and I wonder what more can be improved, right? Like we used dynamic programming, we used pre-computation, we used dictionary for faster computation. What else can be done? Let's just submit again to see if we can beat. Yeah, you see, yeah, this is the randomness of Leetcode. Like in one try, you are like faster than only 10% of people, and then in another try, you're faster than 90% of people. It's just how a little bit dramatic. the Leetcode submission thing is giving you. But anyways, I mean, this is, I guess, an above average solution based on what we see here. And let's take a look at what the solution is telling us and what people do with it. You know, what best practices are there. Uh, you, right, your climbing staircase takes in steps, right? That's the problem. Um, approach one, brute force. In the brute force approach, we take all possible steps combinations at every step. And every step, we're calling the function climb stairs for step 1 and 2 and return the sum of sum of both functions. That is like the brute force recursive approach that we tried. Um, basically, in our first video in the series, it is slow. It is going to um, it's going to perform a lot of computations repeatedly and wasting resource, and that's what it do. The complexity analysis, it goes to time complexity O of 2 to the power of n. Why is that? Because you basically separate each step into two substeps, and then those substeps split into two more substeps. Uh, and how many layers are you going down? You're going down like 5 layers. Why is that? Because, okay, so you're doing that. So yeah, it's understandable. Time complexity is O to the 2n. The recursion tree is gonna go down like that. So that's how you separate them. Like for um, for any stairs, you just split into two options. Like you take one step or you take two steps, and you're basically gonna just scroll it down. Uh, 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 yeah, you're gonna just go down your tree like that, and it takes up to 2 to the power of n. That's understandable. So it's gonna be costing a lot on time. Um, what about recursion with memorization? Um, previous approach, we're redundantly calculating the result for every step. Instead, we can store the result each time in memo away and directly return the result from the memo array whenever that function is called again. This way, we're pruning recursion tree with the help of memo array and reducing the size of recursion tree up to n. Well, so this is now improving the brute force approach with some memory. So when you're basically traveling down the tree, uh, if this calculation is previously performed, you're not gonna perform the calculation again, right? So it's just like calculation on demand. If the calculation is already stored somewhere, you don't do it again, kind of thing. Yeah, you're pruning the recursion tree with the help of memory, uh, right? And complexity drops down to on, but then you're gonna require a lot of storage, a lot more compared to previously. Previously, well, the space complexity was also on. The depths of the recursion tree can go up to n. Yeah, you still need to, I guess, when you travel down, you still need to remember um, what you previously did. So it's about the depths of the tree uh, that is related to the space complexity. In this case, the depth of the tree is the same, but the size of the recursion is reduced from 2 to the power of n to actually n. And okay, that's a little better. Dynamic programming. You have a video. Wow, good. I mean, it's good to have a video, don't you? Yes. Um, as we can see, this problem can be broken into subproblems, and it contains optimal substructure property. And we can use dynamic programming to solve this problem. Okay, one can reach ith step in one of the two ways. Yes. So the total number of ways to reach this one particular step is equal to the sum of ways of reaching this and ways of reaching this. Yeah, that's basically right. Uh, we're gonna let dp denote the number of ways to reach n step, and dpi equals to dpi minus 1 plus dpi minus 2. Yeah, actually this is pretty elegant. Um, it's similar to our way of like splitting our staircase climb problem into subproblems from the middle, but this is, I guess, more scalable. Yeah, more generalizable. So there you go. There you go. There you go. Right. And you're using Java to write it. I think this is a more elegant solution than ours. And the space complexity, time complexity is also acceptable. Uh, right. So yeah, this is potentially a better way of doing it. Fibonacci number. Whoa, really? Uh, right. You're having this deep insight, like looking at this and say, hey, this is the Fibonacci number. And because we have implemented our Fibonacci number, we can reuse the Fibonacci number to calculate it. Yeah, why not? You can just use the Fibonacci approaches, and it shouldn't be more complicated than the Fibonacci calculation. Excuse me. Yep. So it's like a compound Fibonacci thing. Right. And what is Binet's method? Interesting solution which uses matrix multiplication to obtain the nth Fibonacci number. So it's a matrix approach to do the Fibonacci calculation. Because matrix operations can be faster, I believe, than array operations or separate number operations. You can you can make it faster, huh? Does it? Well, it does save a lot on the space complexity, and time complexity wise, it um, it is log n, which is actually less than n. So this is definitely an even superior method by utilizing the matrix to calculate Fibonacci number. It's a further optimization, which is pretty cool. I think this is something, a more advanced approach to with deeper insight. Uh, this is great. Yeah, this is great. Fibonacci formula, closed form expression of the nth Fibonacci number. Oh, there's like a closed form analytical solution for the Fibonacci number. Wow. And it also has this nice time and space complexity. Wow. Yeah, this is really, really good. I mean, we only made it this far as to the DP solution, but we didn't have um, the insight to further improve like the space and time complexity, such as this matrix method or the Fibonacci formula method. Those are some, I guess deep mathematical optimization right there. But That being said, I mean, this is not bad. It's consistent. This thing is still a pass. It's not the best solution that you can see, but it's easy to remember. It's logically very similar to our previous problems. So I guess that's it, guys. So, oh, page not, wait. So here's my summary for today. Today we looked at this, I guess my browser is freezing on me, so I'll just provide a quick summary for you guys. Um, Today we looked at this climbing staircase problem, uh, and the largest takeaway, the biggest takeaway here is don't make stupid mistakes. Mathematically, that's going to cost you a lot of time. As you see, I have done that. Uh, and uh, and then we have been consistently using this uh, pre-computation trick to save ourselves some speed, and then um, we're using dynamic programming, which again is going to be very fast. We're using the dictionary for storage. So, and in terms of the code, um, it's pretty consistent with what we had in in the previous in the previous problem. We have the main function that basically uh, looks up the pre-calculation like this. Uh, After we do the pre-computation with the maximum expected numbers that we can encounter. Uh, yeah. And then here we have the implementation of the pre-computed solutions. And and the trick here, I guess the trick here compared to the previous Fibonacci and Fibonacci problems is that you have to discover this iterative or recursive relationship by yourself. And if like me, you figured this out wrong, you're in big trouble. No matter how well you implemented everything else, if the recursive relationship is wrong, you're in trouble. So make sure when you do this, do it carefully. This is gonna extra caution is gonna actually be worth it, save you much more time later. So this is our recursive relationship here. It's got two cases. Uh, and yeah, in the end we got it, but it was quite a journey, guys. I'm not gonna lie. And thank you guys for sticking along. And I will see you in a next video. Peace.